Hello and welcome to the fifth and last lecture for the Brazilian ICPC Summer School of 2022. In this lecture I'm going to talk about computational geometry, and I'm going to try to convince you that you should try computational geometry problems during contests. Sometimes they seem hard, but I think it's rewarding. I think if you're organized and you practice, you can do them, and I'll try to show you how I go about them. So let's see how this goes. So first, what's computational geometry? So computational geometry is all about answering questions, solving problems that involve some quantity related to geometrical objects. Geometrical objects can be points, lines, circles in many dimensions, so also spheres, planes, and so on. And each of these objects has a representation. So a point may be represented as a pair of coordinates in a Cartesian plane. But a point, this is a two-dimensional object. A point can also be represented as a three-tuple of values in 3 dimensions. So in a computational geometry problem, you will have to work with these objects in a given dimension, and in each dimension there will be a different representation for these objects, different formulas that describe them, and different operations that you can do with them. Therefore, solving a computational geometry problem, so the solution, always necessarily involves 2 steps. The first one is the representation of the objects that you're dealing with. The representation in a computer is crucial to actually do anything with them. So you can draw them on a sheet of paper, you can devise some operation that you want to do, but then you have to put all that in a computer, and that's the first step before you can go to the second step, which is create an algorithm to actually perform the computation that you want to do, calculate the quantity that you're asked, which can be a distance, an area, a length, or some other geometrical quantity. But in order to calculate it, you need an algorithm, and the algorithm will work with the representation of the objects that you have chosen. These 2 things, the representation and the algorithm, are linked. So the algorithm tells you the operations that you want to do, and that tells you which representation is more convenient. For example, there's different ways to represent a line. You can represent a line by 2 points. You can represent a line as a point and a direction. And each of these representations will be convenient in one or other situation. So be aware that whenever you're going to solve a computational geometry problem, first you need to decide which representation of the objects you're going to use. For this, you need to have in mind which operations you want to perform, and you need to make sure that this first step, choosing the representation and working with this representation, is taken care of by your library, your implementation, in a very nice and transparent way. So you want to work in a way that does not limit your ability to design nice algorithms. If the representation gives you trouble, if you have to code a lot to work with these objects, it's going to be hard to keep your code without bugs, and it's going to be hard to design good algorithms. So first, we will discuss how to build a consistent and flexible and powerful library to have it maybe in your notebook to actually solve computational geometry problems in a programming competition where you have little time and you want to do things fast and correctly. But first, I want to say some generic things about geometry problems. So, the advantage that these problems have is clear. So, you will have the ability to visualize anything. So, it's easy to visualize both the problem, the solution, and the algorithm. This is very important. Sometimes, one can have trouble visualizing some particular algorithm. Sometimes on graphs, it's easier, and maybe that's why a lot of people like graph problems, in the sense that you can draw the graph, you can start to think I'm here, then I move there, and so on. Well, computational geometry is even more like this. You actually have geometric objects that you can draw, and you can represent, and you can play with them. So this is a big advantage, and you should never underestimate how much it's going to help. You will be able to draw, and you will be able to see, and you will be able to actually work in this way through your algorithm. So this is the big advantage. The disadvantage, and this is why most people don't even consider solving computational geometry problems when they are in a competition, is they can be tricky to implement. So it may have a tricky implementation, in the sense that it can be easy to have it can be easy to make mistakes. So there's also a lot of possibilities for border cases, right? So for example, you may have points that are aligned, and then there's also possibility of having numerical errors. Of course, the representation of points and so on is finite precision, and sometimes you will have to do operations with them which will start losing precision, and this will lead to numerical error. So these three things can actually be discouraging, and many people just avoid computational geometry problems because of this. Now, I'm here to tell you that actually the ability to solve geometric problems is going to be the difference between good teams that can solve many difficult problems and the excellent teams that will solve the difficult problems and also the geometry problems. So if you want to become, to get the next step in your in programming competitions, you will need to solve computational geometry problems. So this is just a fact of life. If you actually get these, it will mark a difference with all the good teams out there who are just not good at this particular topic because they don't like this kind of things. The other thing that I want to stress is that these disadvantages can be minimized. So what you want to do is to completely minimize the chance of these things cropping up. And this is a result of, on one side, good habits. So good programming habits will lead to you not making many mistakes, not having too many bugs. So good programming habits and a good library, let's say, a good framework. So if you have a good framework where your objects are represented in a clear way and the operations between them are solid, they don't have bugs, and they have been well tested, the tricky part of the implementation, a lot of it will be taken care of by framework that you have in your notebook, and you don't have to think every time, you just copy it. This will also reduce the chance of you hitting bad border cases, and will also reduce the possibility of making numerical errors. This possibility is also reduced if you have good programming habits. You do operations in a good way, and you make sure that things are done in a very straightforward and direct and stable way. So really, the disadvantages that computational geometry problems present, you can minimize them with good habits and a good framework. And once you do this, you will only have the advantage, the easy visualization, and you will see that you will start solving them in competition because they will not be the hardest thing for you to tackle. So let's start by the beginning. Let's consider points. So when you take a point in d dimensions, and I will work mostly in 2 dimensions, but many of the things I will say are just trivially extendable to higher dimensions, I will say that a point P is represented by a pair of values x, y in the Cartesian plane, so x, y are real numbers. Okay? So, of course, you can sum a point P1 or subtract a point P2, and this is x1 plus x2, y1 plus y2, or minus if you're subtracting. Okay? But remember that if you have, let's say, subtraction or addition, then these can be visually seen. So addition is if a point is a vector starting at the origin, then addition is adding one vector at the end of another, right? So this is P1, this is P2, this is P1 plus P2. Subtraction is, of course, P1, P2, and then the vector that goes from P1 to P2 is P2 minus P1. So as I said, operations are now easy to visualize, and you can see any mathematical operation that you define on this on points or vectors, which is the same, is something that you will be able to draw. Now, also you can define the norm of a vector, and this is the length in the Cartesian plane with Euclidean metric. So here it's the square root of x squared plus y squared, right? So for example, the distance between 2 points will be the length of the vector that joins them. Distance between P1 and P2, right? You can also define scalar products. So the scalar product of P1, P2 is the norm of P1, the norm of P2, and the cosine of the angle that they form. And visually, if you have P1, P2, then the scalar product is giving you this length. So the projection of P1 over P2, or the other way around. And you can also define the vector product. Here I will actually say in 2 dimensions, this is the z component of the vector product in 3 dimensions, and this will be P1 times P2 in norm times the sine of the angle that they form. And in 3 dimensions, if you actually want to visualize this, you have to extend the dimensionality. And what you have is, if you have the plane x, y, you add a dimension c, and you have one vector, let's say P1, another vector P2, and the vector product is a vector that is on the perpendicular to both. In this case, since they are in the plane xy, this vector P1 cross P2 is in the z direction. That's why here I'm making explicit only the z component, and it points according to the right-hand rule. So this is theta here. This is theta here also. So these operations have an interpretation, right? And a visual representation, and they will be the basis with which you perform any operation on points. Therefore, you need to have a representation for points that actually allows you to easily perform these operations. Personally, I like to code these operations so that they are transparent, in the sense that they are actual operators in C++. So if you define a simple structure to hold two real numbers to represent points, which is like the simplest thing that you can do with a constructor that just allows you to create a point with given coordinates, then you can represent the sum of them as an operator that actually takes one point, another point, and gives you back a point in the same representation. So you see, when I do this, I can represent operations on points literally writing exactly what I write mathematically. The same can be done for subtraction, for the scalar product, the cross product, the norm, and the distance. So the norm and the distance return real numbers, as do the cross product and the scalar product. But the summation and subtraction return points. So you see, in this way, whenever I write some formula mathematically, when I'm working with the objects with pen and paper, I can then translate it directly to the code and write it exactly the same. Just remember which operator represents which operation. Next up, lines and segments. So lines are just infinite one-dimensional sets of points. Segments will be essentially a line of points that has a beginning and an end. So a segment is identified by its endpoints, P1 and P2. A line you can represent by either 2 points, P1 and P2. So 2 points where the line passes already define the full line, but also you can represent as a point, let's say P, and the vector V. The conversion between these two representations is easy, right? So in this case, P is equal to P1 and V is equal to P2 minus P1. You should note that the same is true for a segment. You can also use PV to represent a segment, keeping in mind that whenever you move in the direction of V, you should never go through P2. And also you should note that the representation of either a line or a segment is not unique. In particular, for example, you can take any two other points to define the same line, or you can take this point and this vector to represent a segment. So the representation is neither unique nor uniquely tied to either a line or a segment. It depends on your interpretation of what's going on. So if your object is a line, you know that it's infinite and you can move either in the direction of V or against it. And if your representation is about a segment, then you know that you have two endpoints. You should move in the direction of V, but only before hitting the other endpoint. So this is important to realize that the representation of most geometrical objects is not unique, is not even unique in type, so you can represent as two endpoints or as a point and a vector, and is basically depends on how you think about this object, not just the numbers, the actual data that you have. So in particular, the point vector representation for both lines and segments leads to what is called as the parametric representation. So the parametric representation of either a line or a segment is such that a point P in that line or segment is represented as P0. So here, let me call these points P0 so that we don't confuse them with an arbitrary point on the line or the segment. So in the parametric representation, you have the start point plus the parameter t times the vector. So this parametric representation is the same, only for lines you have t is any real number, and for segments it's usually the convention is that if you take v to be the difference between both endpoints, then t is on the interval 0, 1. So you see, this representation is particularly useful when you need to move on the line, because now you have a real parameter t that allows you to choose the point that you're going to look at. So whenever, for example, you want to do a binary search and find a point on a line or on a segment, the parametric representation is very useful. It would let you choose a point, and then you can reduce t to choose a closer point to the initial P0, or you can increase t to choose a further away point from P0. But there's also the algebraic representation of a line, right? So a line in 2 dimensions can be thought of as the solution to an equation of this form, right? Where every point in the line satisfies this equation. This has advantages and disadvantages. One of the disadvantages maybe is this algebraic description is not so easy to visualize. It's not so easy to know this is a line unless you already know this is a way to represent lines. And it's also depends on the dimension. So this equation is not the equation for a line in 3 dimensions. This is only in 2 dimensions, right? But it has its uses. And for example, you may want to convert back and forth from one type of representation to the other, depending on what you're trying to do on a given problem. So you may want to write both representations and write functions that convert back and forth from one representation to the other. So just like we did with points, we can define an algebraic representation for our lines in a simple structure in C++, for example, where we provide the constructor with the a, b, and c constants that define the equation. And then we can write a few useful common functions that will allow us to do computations and operations with this line. For example, we can write a function that computes the distance from a point to a line. So the distance from the point to a line is defined so that you go from the point to the line perpendicularly to the line, and it's not hard to see that this distance d is simply a times px plus b times py plus c over the square root of a squared plus p squared, where px and py are the x and y components of the point P here, and this line is described by the equation that we wrote before. So this function takes the point P, the line L, and gives me the result as a distance, a real number. Similarly, you can write functions to compute the line that goes through 2 points. So you take 2 points and you give me a line in an algebraic representation. You can write a function, for example, to get a perpendicular line, which could be useful, for example, if you need to compute the line that is perpendicular to this one and goes through P. So that function will take the line and the point and will give you a new line. You can also take, for example, the line that goes through the midpoint of 2 points and goes perpendicular to them. So let's say you have point P1 and point P2, and you want the line that is perpendicular to the segment that joins them, and so on. So you see, once you have an object, you can start thinking of common operations that that object might be subjected to, and you can include in your notebook, in your library for computational geometry problems, many of these things where you have tested and made sure all the formulas are correct, and you don't need to code them during the competition. Just to get this point through, let me show you a couple more things that you can define with lines in the algebraic representation. So for example, you can define a function to determine whether two lines intersect, and if they do intersect, give me the resulting point. So two lines can either be parallel and they don't intersect, so this means zero intersections. They can cross each other and have one intersection, then there is a point, or they can be one over the other, and then there's an infinite number of points that belong to both lines. So writing a function that distinguishes these three cases, and make sure that it finds the correct answer without all the special border cases, without forgetting in particular. It's easy to forget that sometimes lines don't intersect or intersect in any point. So these two are border cases that you better be sure that your code deals. Well, it's nice to have this pre-coded in your library, or some other things that maybe are not as easy to remember. So for example, you can write a short function that computes the bisector of an angle. Let's say you have some point, which here I call PC, you have P1 there and P2 here. There is an angle that is formed by this vector and this vector, and there is a line that bisects this angle, cuts it in half so that this part is equal to this part. And obtaining this line, well, it's just a construction using the things that we defined before. So you know how to do this with a pen and paper probably. You learned at school with writing perpendicular lines and writing the line that goes through some points. So you use the functions that you defined before to actually build more and more complicated infrastructure for you to use later on. Okay, so I hope to have convinced you that choosing representations for objects and having them implemented in your notebook for easy use during a competition is important and will help you a lot. I won't be giving explicit representations for various other objects like circles and so on. You can find those in books or in references, and well, you can ask me also, but I assume that okay, you know Euclidean geometry, and you can work this out for yourself. You can make sure that the formulas that you get are correct, and you consider all cases. Let me now move on and show you some examples of things that you can do involving these structures. So the first example I want to deal with is the intersection of planes in 3 dimensions. Okay, so this example is in 3 dimensions, where a plane in 3 dimensions, I can think it is given by a point, P0, which is on the plane, so P0 belongs to the plane, and a normal vector, N0, which is orthogonal to the plane. So in this representation, one way to visualize it is if I have the plane like this, I have the point P0 on the plane, and the vector N0 is perpendicular, so the angle here is a right angle. There is also an algebraic description of the plane, which we can write as any point on the plane should be orthogonal to the normal. So let us parse this. Any point on the plane, so for example this one, has a vector that goes from P0 to it, which is this guy here, so that's vector there, and it should be orthogonal to the normal of the plane. And remember, we defined the scalar product here as being the norm of one, so P minus P0 norm times the norm of the other guy, which in this case is the normal, times the cosine of the angle that they form. And since we have that both the difference here and the norm of the normal here are non-zero, then the only possibility for this to happen is that the angle is a 90-degree angle and the cosine is 0. So this algebraic representation comes from this equation, and if you parse it out, you can see that it means that this is ax plus by plus cz plus d equal to 0, where a, b, and c here and d are related to the constants p0 and n0, defining the point and the normal to the plane. More explicitly, n0 contains as its components a, b, and c, and the constant d is nothing else than minus p0 scalar product n0. So again, we have two representations for planes, the point and normal or the algebraic. We have a way to convert between them, and we are going to ask now, how do we find the intersection of two planes? So let's start by assuming that the planes are not parallel. So if the planes are not parallel, that means that they intersect on a line. Now, excuse my bad drawing here, but maybe this can be made clear if I draw the intersecting line here in some other color. So if the planes are not parallel, they intersect in a line, and we can easily check whether they are parallel by just checking whether the normal vectors are parallel. If they are, they either have no intersection or they are actually the same plane and they intersect at all points. So let's assume for now that they are not parallel. Then the line, because it belongs to both planes, the line has to be normal to both n1 and n2. So the line is orthogonal to n1, defining the first plane. So n1 is the normal to this guy, and there's an n2 that is normal to the other guy, so it has to be orthogonal to both. Therefore, a vector parallel to that line, as we saw, we can take it as the cross product of these two things. So we saw that the cross product of two vectors in 3 dimensions is a vector that is orthogonal to both, and then v is in this direction. If we want a parametric representation of the line, then we only need to find a point that is on the line. Once we have a point and a vector, we have a line. So, how do we find this point P belonging to the line? Well, one trick that we can use here is define this point as the point on the line that is closer to some arbitrary point. So let's say that we have a coordinate system here, x, y, z. We can always think of this line as being defined by the point, maybe around here, that is closer, let's say, to the origin. So that minimizes this distance. Okay? The only thing that we need is to find a definition that gives us a unique point. And clearly, if I draw a line in 3 dimensions, then there is a single point within this line that minimizes the distance to any given point in space. So now the problem is all about minimizing. So we want to minimize a distance from the origin. So the distance, let's call it distance square, is x squared plus y squared plus z squared. This is the distance from the point x, y, z to the origin under some constraints. So the constraints are this point, the point is x, y, z. It needs to be on both planes because it's on the intersecting line. So P minus P1, the point defined in the first plane, scalar product, the normal to that plane, is 0, and also P minus P2, the point defined in the second plane, and the normal to the second plane, that's also 0. So this is a function to minimize, and these are constraints. We can then use the Lagrange multiplier method to solve this minimization subject to constraints. This method basically states that we need to define the function f, which depends on the coordinates of the points x, y, z. And because we have two constraints, we will add two multipliers, mu1 and mu2. And this function will be defined as the quantity that we want to minimize, in this case the square distance, which is just the norm of p squared, plus each constraint multiplied by the equation that we require to solve. In this case, mu1 is multiplied by p minus p1, scalar product n1, plus we have another constraint for the other plane, p minus p2 times n2. So this function depends on the coordinates of the point. Here you have p. It depends on two more quantities, variables, which are the Lagrange multipliers. And therefore we have 5 unknowns and we need 5 equations to solve them. Let me, before moving on, make this function more explicit. I'll omit the arguments to save some space. So this function has the distance x squared plus y squared plus z squared, and then you have mu1 times x minus p1x times n1x plus and so on for y and z, and then mu2 times x minus p2x n2x plus the same thing for y and z. According to the Lagrange multiplier method, we need to solve, to minimize our function, the following equations. First, the derivatives of the function with respect to the points should be 0, and also the derivative of the function with respect to the Lagrange multipliers. So the derivative of f with respect to mu1 and the derivative of f with respect to mu2. More explicitly, these will give you something like this. The derivative of f with respect to x is nothing else than 2x plus mu1 with n1x. and also mu2 times n to x. For the derivative of f with respect to y, we have something similar, 2y plus mu1 n1y plus mu2 n2y. For the derivative of f with respect to z, 2z plus mu1 n1z plus mu2 n2z. And the equations that are given by the Lagrange multipliers are simply the equations for the plane. So p minus p1 times n1 scalar product is 0, and this guy is p minus p2 scalar product n2 is 0. Thus we have 3 equations here, 2 equations here, 5 unknowns, so we have 5 equations with 5 unknowns, and we see that the unknowns appear linearly in each of the equations, right? And here you have p, and there's no Lagrange multipliers. So essentially, this is a set of 5 linear equations over 5 unknowns. By now, I should have convinced you that solving linear equations is easy. You just write them in matrix form and you solve them using Gauss-Jordan elimination. So in matrix form, the previous equations are just 2, 0, 0, 0, 2, 0, 0, 0, 2. And then you have n1x, n1y, n1z. The same thing here, n1x, n1y, n1z, and n2x, n2y, n2z. The same here, n2, n2, n2y, and simply zeros there. So this is the matrix. The variables are x, y, z, mu1 and mu2. You can verify that if you multiply these two, you get the equations where on the right hand side I have to put 0, 0, 0, p1 dot n1 scalar product, p2 scalar product, n2. So in your code, the only thing that you need to do is put this matrix directly in Gauss-Jordan elimination, invert it, and find the values of x, y, z. This is going to be very fast. It's only 5 equations. It's going to be very precise. It's going to have a great numerical accuracy, and therefore this is a very nice method to have pre-implemented in your notebook. Before moving on, let me mention that in a previous contest I proposed the problem called Joe's triangular gardens, which stated that there was a triangle and you want to find the ellipse that touches the sides of the triangle and is tangent to these sides at the midpoints of these points. So if this is P1, this is P2, this is P3, these points are the midpoint of P1, P2 and P3, and the ellipse touches these points. And okay, I'm going to have a lot of trouble drawing this, but you can see it would look something like this. Now, I don't really remember if people solved this problem, but my solution is all about writing equations that you can solve again using Gauss-Jordan. So there's one equation stating that the point should be on each side and the midpoint of the triangle. Those are 3 equations. There's other equations that state that these should be tangent, so the tangent to the ellipse should be the same as the slope of the side of the triangle, and these are 3 more equations, but one of them is redundant, and actually if the triangle is a rectangle, one of them will not provide an actual equation, and therefore you have again 5 equations, and the equation for the ellipse is a conical, so it also has 5 unknowns. Then you can just solve for the parameters of the ellipse, and then you can just, on pen and paper probably, find the foci of this ellipse and just provide the answer. So this was another problem where it was useful to have a few predefined things and then use Gauss-Jordan to just write equations to solve the problem, and then do some geometric transformations, which you can do on pen and paper. Okay, so we have seen how to represent basic geometrical objects in the computer. We have seen that it's important to define operations between them. Then we saw that we can build more and more complex operations with these objects until, for example, you can do pretty complicated stuff like finding intersection of planes in 3D and these kind of things. Now, we should move on to the part where we actually design algorithms. So for now, we have been just dealing with the basic structures that we use when we build algorithms. Now, a classical problem to consider in computational geometry is the closest pair of points. The formulation of this problem is the following. We have a set S, which is a set of points, pi, and these are n points, let's say, in 2 dimensions. Then we want to find the quantity delta S, defined as the minimum when I is different than j of the distance between pi and pj, so the norm of their difference. And before going on, I should mention there is a lower bound on the complexity for the solution to this problem. This lower bound is given by the element distinctness lower bound, which basically is the same as asking the question, is delta of S equal to 0? So if this question can be answered, we can know whether 2 elements in this set are distinct or not, they are different points or not. Only the norm between 2 points is 0 only if these 2 points coincide, and the lower bound on the complexity for this problem is n log n. And this lower bound is achieved by many well-known algorithms. In particular, it's achieved by a sweep line algorithm that is a classical algorithm, and it's an example of the use of the sweep line technique, which in 2 dimensions is one of the most useful techniques that you can use in geometrical problems. So it's just the simple idea of imagining a line that moves, let's say, from left to right or from top to bottom, or around a point in the plane, and considering events that occur as they cross this line. So this is I want to stress this is a very important technique to know. It solves lots of problems. It's the basis of many algorithms, and I encourage you to go and look at the solution of the closest pair of points problem from this perspective. It's very nice. It's an exercise in analyzing algorithms also, but there's also other solutions. There's, for example, a solution which is essentially a divide and conquer solution, sort of similar to merge sort. You divide the plane in halves, and you then combine the halves to find the minimal distance. But in this lecture, I want to mention a less well-known algorithm that is actually not satisfying this bound. So the algorithm I'm going to present is ON, and at least in expected time. And while this seems completely counterintuitive, right? We said there's a lower bound, and I'm saying that I'm going to present faster than the lower bound algorithm. This algorithm is actually cheating, so the lower bound is achieved on a computational model that does not use the crucial operation floor. So you see, sometimes you can escape lower bounds that are mathematically proven just by adding some special operation that was not considered in the computational model where this lower bound was proved. In this case, I'm going to use the floor function, and it's amazing that with just this addition you can change the running time to ON, and this is why I like this algorithm, and hopefully you will learn a different technique that is different from the sweep line, which you maybe already know, and the divide and conquer technique, which also solves the closest pair of points problem and many other computational geometry problems. So let's see how this works. The technique I'm going to use is called sieving. So I'm going to define a sieve which will filter the points. It will discard isolated points which are far away from all other points in the set, and the sieving process may not be perfect, but first it will give us an approximation to delta of S. So we get an approximate value of delta of S, and then we will go to the exact value delta of S. So there's two things that are interesting here. One is the sieving process, the fact that you can define sieves that are further and further restricting your set of points. And the second is that this is an algorithm that first gives an approximate solution and then produces the exact solution. So these are two techniques that are common in computational geometry. They are also useful for other problems. So sometimes it's nice to think about these kinds of tricks to get exact solutions from inexact ones, or to reduce the problem size as you move along, so that your complexity doesn't blow up. So how do we implement the sieve? So the points that we have, let's say, are on the plane. Then the sieve is going to be implemented through a grid. Let's say that we have our x and y coordinates for each point. We will define a grid in this plane that is equally spaced in the x and y directions. So we have many cells both in the x and the y direction. So we have these squares that partition our set of points into smaller groups. This is L, the side of the boxes that I'm creating. The whole idea of this algorithm is that some boxes will contain many points, and points that are closer together will tend to be in similar boxes. Now, of course, some points that are very close together may end up being in different boxes, but definitely two points that are far apart, let's say this point and this point, will not go in the same box, and therefore if a point is far away from all others, we can discard it and sort of stop considering it, because it will definitely not be within the pair of closest points in our set. This is the idea of our algorithm, plus defining smaller and smaller grids to produce finer and finer sieves. Let us see how this works. First, let's see how we define grids. As I said, we had the x-y plane. We will now take a mesh of size L on each direction, size L here in the y direction too. And the way to do this in practice is to assign to the point xy will be assigned to a cell which is just x over L floor, y over L floor. So while points are represented by simply real numbers, the grid is represented by pairs of integer numbers. And it's not hard to see a few properties that this grid has. The first one I want to mention is that the maximum distance between a point in a given cell and a point in a neighboring cell is bounded by this diagonal. So if 2 points are on neighboring cells, they cannot be further apart than this length. Let's write that down. Let's say there's a point P and another point we call P prime. If the distance is greater than that diagonal, and that diagonal is of length 2 square root 2 of L for Pythagoras theorem, then point P prime is not in what I will call the neighborhood of P. So let me be explicit. The neighborhood function is such that it gives me all the points that are in a cell that is either my cell or the immediately adjacent cells. So, for example, the neighborhood of any point in this cell is any point that is on these cells here. So I'm counting also the diagonals. Then the property is that if 2 points are further apart than 2 square root 2L, then they cannot be one in the neighborhood of the other. Another property that we have is that if the distance between 2 points, let's say P and P prime, is smaller than L, then definitely P prime belongs to the neighborhood of P. And this we can see pretty easily if 2 points are, let's say I have another point, and the further it can be to the left, this is P, this is P prime, the further it can be to the left of P, here is L. If I bound this to be L, then it needs to be in an adjacent cell. It cannot go all the way to away from the neighborhood, either to the left or to the down, to the right, or up, right? If this distance is bounded, I always stay within the neighborhood, right? So let me stress this concept. The neighborhood of a point is actually the neighborhood of the whole cell of that point, and it includes that cell and the 8 cells that are around it. So it's in total all the points in those 9 cells. Now the question is, what happens when we have P minus P prime at a distance that is at the same time less than 2 square root of 2 L but greater than L? So we have considered all the other cases. These are the cases where we don't know whether P prime belongs to the neighborhood of P or not. Now that we have defined the neighborhood of a cell and we know the properties of our grids, we can start filtering. So I said this sieve works by filtering points and reducing the amount of points that we are considering. So we will define the set S1 to be our original set S, and this one we said has n points. The set Si will be the result of filtering, and this is a filtering function, the set Si minus 1. So as we progress, we will create a sequence of sets of points, and the property that this sequence will have is that the set at step I will be contained in the set Si plus 1. And in fact, it will be contained and will not be equal, so their number of points in each set is decreasing. This will go on for I from 1, our original set, and onwards until we reach a terminal set. This terminal set is defined such that the filtering function on the terminal set is the empty set. So after the last step, no points are left in our sets. So how does the filtering work? First, you choose a random point in the set. So choose, I will call it P star, randomly in the set Si. Now, once you have chosen this point, you have to compute the minimum distance from this point to any other point in that set. So I will call this distance d of P star, and this is defined as the minimum over all points P that belong to set Si but are not the point that we have chosen, P star, and the distance is just P minus P star norm. Next, we will build a grid. So we grid the space with a grid size L of size d of P star, and here we will introduce a factor of 3, and you will soon see why this factor needs to be there. The final point is we discard points. Which points are to be discarded? Well, we discard every point that has the following property. If P has a neighborhood of P that only contains the single point P, then we discard this point. This 4-step process is repeated each time the filter is applied to each Si. Now let's analyze this filtering function. First, which points are discarded? So we just gave a rule. We said if the neighborhood of a point is contains only that point, then we discard that point. What does this mean? Well, here we should remember that if P minus P prime in norm was less than L, then definitely we knew that P prime belonged to the neighborhood of P. But if a point gets discarded, the neighborhood of P is just P. Thus, we know that for all P prime, we have that P minus P prime is greater than L, which we should remember was set the distance from P star to the closest point over 3. But then, who is left? So what are the points that survive this process? Well, it's those points which have at least one point that is closer to the P star over 3. So in order to survive the filtering process, you have to have points that have a closest point that is closer than the closest point to P star over 3. This means that d of P star for successive iterations of the filtering process is a decreasing sequence. This, of course, is very important because if the sequence of d of P star decreases, eventually, because it's bounded below by the closest distance between any 2 points in the set, then necessarily it needs to terminate. So our sequence and our algorithm terminates. Now let's see what happens when this actually terminates. Now in the last step we have a set Si with some number of points, and we know that then if we take the filter of Si, we get the empty set. What does this mean? First, this is telling us that the minimal distance of our original set is at least as small as the distance that we actually found for the point P star at the last iteration. So this is obvious, right? We found in the last set 2 points that were at the distance d of P star I, therefore we know that this is at least the minimal distance. Maybe we can get shorter distances, but certainly this is achievable. Now, there is another bound on the other side that we can write. How do we find it? Again, we remember that if P and P prime are at a distance less than L, then P prime belongs to the neighborhood of P. However, we have found in the last step that there are no 2 points in the same neighborhood, because otherwise this wouldn't be the last step. So this means that when there are no 2 points in any n of P, then all the distances P minus P prime should be greater than L, which was d of P star at the last iteration over 3. And of course, because this is all the distances, then this is also satisfied by the minimal distance in particular. Thus, we have that this is bounded by d of Pi star over 3. This result is a bound on the minimal distance on our original set. This is an approximate solution to the problem. If we are happy with this approximate solution, let's say we don't need an exact solution, then we could stop here and just say, well, the distance is within this range. I've achieved what you asked me with a certain precision. But actually in ICPC, normally you are asked to provide exact results up to numerical precision. So this approximate solution is not enough. Now, how do we turn an approximate solution into an exact solution? We know that d of P star I over 3 is smaller than the minimal distance in our original set. And this distance is at most the distance that we found in the last set. So what we're going to do is we are going to use this part of the inequality to build a grid with L equal d of P star I. Then what we know is that if P minus P star is less than L, then as usual P prime belongs to the neighborhood of P. But now we know that the closest pair of points satisfies this condition. Its distance is less than the grid size. Therefore, the closest pair of points is in the same neighborhood, right? So this is the key. Both points are in the same n of P. Then we can just check all neighborhoods, all pairs in each neighborhood, and we directly compute the closest pair of points. The only question is how many checks this is. You would think that this is O(n) squared, so you can have up to n points in the neighborhood, so then checking all pairs is O(n) squared and we've gained nothing. But no, this is actually not true. What we know, and we know it because we have this other side, we know that the minimum distance is larger than 1/3 of the length of our grid, and this means that all points are at most at that distance, so you cannot have many points in the same neighborhood, and therefore there are actually O(1) points in the neighborhood of any other point, and the checks are just O(1) squared, which is O(1), and everything actually works perfectly fine. So this is the same sparsity condition that you use in a divide and conquer approach to finding the closest pair of points, but here we are using it only at the final step to transform the approximate solution that we found in an exact solution. To analyze the running time then, we don't really need to take care of this step. We know this step is essentially O(1) for each neighborhood, and therefore this will lead us to, because there are at most O(n) neighborhoods, an O(n) last step. We need to analyze, however, the first filtering steps and make sure that we are not doing too many of them. But the analysis of the filtering process is actually pretty easy. So in each step we choose a random point. Here I called it P star I. We computed the distance from this point to all other points. This is O(n), and we discarded any point that had a larger distance. So we discarded points that had d of p larger than d of pi star. Now, if we had ni points at the step I, so n1 is the original number of points, and then each time we have less and less points, then the expected number of points at step I plus 1 is nothing else than half the number of points that we have in the previous step, because half of the points will have larger distance than pi star and half of the points will have smaller. Now, this is probabilistic analysis because this is a randomized algorithm, so we will reach an expected running time at the end. This means, of course, because each time you halve the number of points in your interval, that this is n1 over 2 to the I, and n1 was actually n, so this n 2 to the I. Then the expected running time, which is just a sum from 1 to the last step of O and I, is nothing else than O of the sum of n over 2i for all i's, and this of course is O(n). Because the last step was also O(n), our algorithm is finally O(n) in expected time. So we've reached the end of this lecture. I hope that the randomized algorithm for the closest pair of points was interesting. There are some implementation details that if you're going to try and put your hands in the dirt and code this, then you're going to have to figure out. In particular, dealing with the grid without introducing any logarithmic factors will require you to use, for example, unordered maps in C++, so that these hash maps will be O(1) expected time to obtain all the points in a given cell or in a given neighborhood. And all these details I leave you as an exercise, But the whole point of this description of this algorithm is for you to think also in different terms. So we are used to thinking of that any computational geometry problem should be solved by a sweep line algorithm, or if you're very crazy, it's a divide and conquer algorithm, or some standard thing that you've already heard about, like, I don't know, the convex hull. So I'm trying to convey the idea that there's also other types of algorithms, other ideas that you can implement. Sieving is a very nice one, and I hope the next time you see a computational geometry algorithm, you will maybe try to think about sieving if it deals with many objects and you're trying to find certain ones that satisfy a given property or something like this. That being said, if you have any questions or any kind of thing about this lecture that is unclear, please ask questions. So as usual, I'm available during the Q&A sessions or by email, and I hope to maybe produce some extra material, maybe a short explanation of recursive descent parsers. But in any case, I would like to thank you for following these lectures, for doing the contest. I hope you have enjoyed this week. So really, thank you. It's been a pleasure, and I hope you do great in your future in competitive programming.